All right, what's going on, y'all? Another problem, displacement slopes, right? Just your displacement vector, force is equal to kx. We got to get the displacement vector, the x vector. Then we get the force vector, and then we'll get the forces in each elements, and then the shear and bending. Let's go ahead and get started. All right, so in this case, we got two elements, right? Element number 1 between nodes 1 and 2. And element number 2 between nodes 2 and 3. At node 2, you have a downward force of 20 kilonewtons. At node 2, you also have a twist happening right at the center, right? Pretend like a beam is coming out and it's causing nothing to twist. It could be anything, right? But just trying to give you guys an insight as to what's kind of happening here. It could be a design problem, right? You have a force and a moment at that node. Nothing going on at 1, nothing going on at 3. So you're able to discretize the system in 2 elements, right? To get the stiffness of each element, you use this right here. K is equal to EI over L cubed. This is just from the book, right? From the chapter. So this is the stiffness matrix that you're going to be using for every single problem in your homework and exams that relate to transversely loaded beams, okay? So in this case, since they're the same length, they have the same moment of inertia, which is 4 times 10 to the negative 4. And then they also have the same modulus of elasticity as steel, right? 210 gigapascals. So for both members, our EI over L cubed is going to be 3,100,000, this number that you see right here, okay? Newtons per meter. That's a stiffness value, okay? So remember, at the end of the day, it's just force is equal to kx. This is your K matrix. Your X vector is going to be your displacement and rotations, which is what you're finding, right? And then your force vector is going to be the reactions, okay? Forces in each element come after. We'll get there eventually. So step number 1 on these problems, right? You start with your boundary conditions. So this is where the majority of FEA happens. You got to know this. This is either going to make or break you on the exam, right? You got to know how to set this up before you move on. If not, it's going to mess up your whole problem. And after that, it's just algebra. So this really is the biggest part of FEA, knowing how to identify the boundary conditions and then your external forces and moments in this case. So we know at node 1 and 3, they're both fixed. So no matter how much force you put along the beam anywhere on any of the 2 beams, you're not moving that thing, right? So V1 and V3 are 0. Because they're fixed, your angle of rotation at these 2 nodes is also going to be 0, okay? So if you apply a force going down and then a rotation at node 2, you're going to displace some number and you're also going to rotate some number, okay? So V2 and V2, we don't know. Even if you didn't have a moment, you still would have some rotation, right? Your moment would just be 0 in that case. And I told you guys on all the other problems, you either know one or the other. You never know both, and you never know just one. If that I don't know if I said that correctly. What I'm trying to say is, since we know the boundary conditions at V1, Phi1, V3, Phi3, that means we don't know the force or the moment at 1 and 3, okay? Because we don't know V2, Phi2, that means we know force 2 and moment 2, okay? That's 20,000 and 20,000. So just FYI, that is the trick. You either know one or the other, but you never not know both, and you never not know none of them, if that makes sense. I hope you guys understand what I'm trying to say, but you'll see here. Let's go ahead and go to the step 2, global equation, right? You have your force vector is equal to your K vector, K matrix, which is just your stiffness matrix, your global stiffness, and then multiply it times your displacement vector, okay? So what happens here is you start combining the stiffness for both elements. So look, element 1 is between nodes 1 and 2. So this K matrix goes from V1, Phi1, V2, Phi2, right? V1, Phi1, V2, Phi2. So that's right here. So you just do V1, Phi1, V2, Phi2, V1, Phi1, V2, Phi2. Okay, so this 4 by 4 matrix right here, that belongs to element number 1. And then the other one is between nodes 2 and 3, right? So that one's V2, Phi2, V3, Phi3, V2, Phi2, V3, Phi3. And that goes here, okay? This 4 by 4 matrix. Now, these 4 overlap on both, right? Because they both share node 2. So you just add them, right? This 12 would get added to this 12 on the second. So how about this one on? For element 1, this 12 gets added with this 12 on element 2. And that's this position. For V2, you'll get 2 12s. So that's how you get this 24. On this one, the next one, the one right next to it, you have a negative 6L here, and then the 6L here is going to give you a 0. And it's symmetrical, so this one's also 0. Same thing. Then this 4L squared is going to get added with this 4L squared. Now just go ahead and plug them, right? Do each one separately, and you'll see that these 4, you got to add them, because you're going to have the same spot, right? Because they both share node 2. So once you do that, you'll have your global stiffness matrix. Remember the 3,000,000, 100,000, whatever. Outside, don't forget that. That's important, right? That's the EI over L cubed. That's right here. And then you go ahead and start applying your boundary conditions. So we know V1, Phi1, and V3, Phi3 were 0. So I went ahead and plugged them in, okay? Once I do that, I could go ahead and just cross them out. V1 is 0, Phi1 is 0, V3 is 0, Phi3 is 0. So that's the lines that you see in the matrix. And I do the same going this direction. V1, Phi1, V3, Phi3. Then at the end of the day, you're just left with these 4 elements that didn't get crossed out, right? Little values, okay? Keep those in mind for now. Let's go ahead to the force vector and the moment vector. Remember, I said you either know this one or this one, but you never know both, and you never not know one. Okay, so you have to know either this one or this one. Okay, in this case, we know V1 is 0, so that means we don't know F1y. We know Phi1 is 0, so that means we don't know M1. We don't know what V2 or Phi2 are, but we do know that there's negative 20,000 coming in, and there's a counterclockwise 20,000 going around, right, at node 2. So you see, we don't know these, but we know these. And then V3 and Phi3, these are 0, so that means we don't know these, okay? Now let's go ahead and go down to the systems of equations, right? So once you got that part, you could go ahead and start assembling the equation. For now, let's just focus on V2 and Phi2. First, you find this. Then once you find these two, you'll know all your 6 displacement values, right? 1, 2, 3, 4, 5, 6. And then you're able to find the rest, okay? So it's real easy, right? Just focus on these. That's why I cross them out at first, once I know they're 0. So negative 20,000 is equal to 31111, that number right there. Okay, so negative 12 times 0, which is 0, minus 6L times 0, plus 24 V2, plus 0 Phi2, plus 0, 0. So that's how I got the first one. And the next one is positive 20,000 is equal to that number, the stiffness, right? 31111. 24 V2, no, I'm sorry, 0 V2, 8L squared Phi2. So that's how I got that. And once I do that, I get my V2 and Phi2, okay? So now that I have those two values, try to make sense of it. You obviously you don't know if this answer is correct or not, but you could use intuition to help you out, right? V2 is negative. Does that make sense? If you apply a force here going down, yeah, the node 2 is going to come down, right? You're pushing the beam down. So the negative alone gives me an intuition telling me, hey, kind of makes sense, okay? Phi2 is positive. This one's kind of tricky because I guess it makes sense, right? The reason it's tricky is because you have a moment added. So you have a force. Imagine you just had the force going down. Pretend the moment's 0, okay? If you had a force going down, then your beam is going to look something like this, right? That angle that it makes with the x-axis is positive. So I guess this number makes sense, okay? Yeah, didn't mean for you to see that. So that number is positive here. And yeah, if you're adding a twist to it, you're helping it deflect even more, right? So yeah, I guess that number being positive also makes sense. So that's how you're able to verify these numbers without actually verifying the magnitude. You could at least verify the directions. And that should give you an idea if you're going the right direction. If I got a positive number for V2, that would not make sense whatsoever, right? But now you get the idea. So let's go ahead and just keep going, right? Now that we have V2 and Phi2, now we're able to find F1y, M1, F3y, and M3. So let's go ahead and do that. We're right here. F1y, same process, right? Now, forget about these crossed out lines. Now we need them. F1y is equal to 12V1, which is 0, plus 6L Phi1, which is 0, minus 12V2, we already know V2, plus 6L Phi2, we already know Phi2, plus 0V3, plus 0 Phi3. That's what I got here, okay? And I did the same for M1. M1 is equal to 3, 1, 1, 1, 1. And then minus 12 times 0, minus 6L times 0, time, I'm sorry, I wrote the wrong one. 6L times 0, 4L squared times 0, minus 6L times V2, which is that, plus 2L squared Phi2, which is that. I already know V2 and Phi2, and I do the same for the other ones, right? So I just plug in V2 for all of them, Phi2 for all of them, and you get these numbers right here. Now, you don't get perfect numbers, but you have to like understand what the hell's going on, right? 15,002, that's just an even 15,000. And if you're not comfortable doing this, just keep it at that number. You're still going to get the answer right, okay? But in this case, for F1y, we get 15,000. M1, you get 20,000. F3y, you get 5,000. M3, you get negative 10,000. Now let's go ahead and verify these numbers. Now these we could somewhat verify them. Just use statics, right? So when you use statics, before we go to statics, just look at the numbers for a second. F1y and F3y. Summation of forces in the y direction. This is quick. You don't even need to write this down. You have 20,000 going down, so that means you have 20,000 going up, right? Is that true? Yeah. 15,000 going up at node 1. 5,000 going up at node 3. That's 20,000. That makes sense. M1, to verify these, you do, well, to verify all four, you use statics, but the forces is the easiest. You just do summation of forces in the y, okay? So we verified those. That's 20,000. Now let's go ahead and do this. That's what I did here, right? Summation of the forces in the y is 5,000 plus 15,000 minus 20,000 equals 0. Check mark. Cool. That made sense. And then let's do summation of the moments. You have the reaction, positive 20,000. So that's a clockwise moment. Counterclockwise, I'm sorry. Counterclockwise. You have a counterclockwise already given. Okay, 20,000. And then you have a clockwise moment. I don't know what I said here. I meant counterclockwise, okay? And then you have a clockwise moment going here, 10,000. Now, let's go ahead and take the moment about any point that you want. And given this diagram right here, you should be able to check it out. So I can't remember how I did it. Let's see. For all the moments that are just visible, you just add them, okay? In this case, 20,000, that's that one. 20,000, that's this one. Minus 10,000, that's this one. And it seems like I took a moment about one of these 2 points. I can't remember which one. 3 minus 20,000 times, I took it about 0.1, okay? So I took this 20,000, I multiplied it by the distance. So it's minus 20 because it does a clockwise moment, about 0.1, right? So minus 20,000 times 3 plus 5,000, right? This 5,000 times 6, your distance to 1. And you could have taken it about 0.3. You could have taken it about 0.2. Point is, you're not going to use one of the forces. In this case, I didn't use force 1 because I'm taking the moment about that point, right? If I would have done it about 0.3, I would have done this 20,000 and this 15,000, okay, at node 1, doing the moment. I could have taken it about 0.2 and used these two moments, forces, to calculate the moment, however that would have been. Point is, we verified it's equal to 0, so that means all this is correct, okay? So now that that's correct, we verified all the force vector, and the displacement vector. So now we're gonna find the forces in each element. Easy, right? We got 2 elements. This one's between nodes 1 and 2, and this one's between nodes 2 and 3. And we're gonna use this K matrix, not this one. You're not gonna use these 16 values, okay, for element number 1. you're going to use this one right here, 12 4L squared. I don't want you to use 24 8L squared, 0 and 0. You have to use just the beam stiffness, okay? And then you're going to use, so in this case, we're going to do element 1. It goes from nodes 1 to 2. So let's go ahead and do that here before I show you the answers, right? F1y, M1, F2y, F2, M2. That's element number 1. It goes between nodes 1 and 2. It's equal to the stiffness. Look, 12 4L squared, negative 6L, negative 6L. I didn't use 24 0 0 8L squared. Okay? So once you got this matrix here, the stiffness, you know V1, Phi1, you know V2, Phi2, right? We calculated those on the previous page, so just plug them in and do the same thing. So I'm going to just show you the answer right there. F1y is equal to the stiffness, 3111. And then it's 12V1, 6L Phi1, that's 0, 0, right? Because these are 0. Minus 12V2, we know V2, 6L Phi2. Plug in the numbers. Boom, you get 15,000 for F1y. Let's do one more, F2y, okay? F2y is equal to 3111. And then it's minus 12V1, which is 0, minus 6L Phi1, which is 0, 12V2, 12, this one's V2 right here, minus 6L times this number right here. And then you get these numbers, boom and boom, you'll get F2y is equal to negative 15,000. So do that for all 4 of them and you'll get these numbers, okay? Now, we'll verify these numbers, but first you have to calculate every single element's forces in each element, okay? So we did the first one, now let's do the second one, right? Second element is between nodes 2 and 3. So same thing, right? You use a 12, 4L squared, 6L, 6L, okay? You don't use 24, 0, 0, 8L squared. Once you do that, now V2, Phi2, V3, Phi3. Notice how these just shifted up, right? Because this one that went from nodes 1 to 2, now you're going from 2 to 3. So these two went up, and then V3 and Phi3 are right here. So same thing, right? You'll have F2y is equal to this, 12V2, 6L Phi2, minus 12V3, which is 0, plus 6L Phi3, which is 0. Then do all that, right? You set it equal to each other, and you get F2y is equal to that. Repeat it for the other ones, and you'll get these numbers. It's already there, so you can always compare your answers here, no big deal. But once you have these, now you can verify it, okay? So the trick to verifying these is once you have all of them, add all the little force values with each other, and they should equal your big force values, okay? So this is what I mean. In this case, F1y. How many F1y's do you see? It's just this one. Nope, nope, nope. Nope, 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 nope. So F1y has to equal my big F, okay? My big F1y. So let's go ahead and check that. Is that true? F1y was 15,000. Does that equal my little F1y? Yeah, it does. So that means we're good. M1, add all the M1s. In this case, we have this one. Nope, 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 right? So my big M1 should be equal to this one, 20,000. Is that true? Yes, it is. F2y's, it's usually the ones that get shared, right? So F2y's. So F2y is negative 15,000 here, and then we have another one here, negative 5,000. Add both of them, you get negative 20,000. Is my big F2y equal to negative 20,000? Yep. Yes, it is. It's right there. What about M2? M2's right here, and there's another M2 right here. 25,000 minus 5,000, that gives me a 20,000. And yep, at node 2, you have a positive 20,000 clockwise. Finally, F3y, we see there's no other F3s except this one, and there's no other M3s except this one. 5,000, negative 10,000. And boom, 5,000, negative 10,000. So cool. That means our answers are correct. And let's go ahead to the final step, shear and bending moment diagrams. Now, it looks complicated, but if you know how to do these from statics, you'll be fine. We'll go ahead and do it real quick. We'll start from scratch, right? So in this case, let's do shear, okay? Now, we already got the beam drawn pretty much with all the what do you call it? The external forces and moments. or the internal forces and moments being produced, right? The externals and the internals. So in this case, let's do shear. Bending moment does not affect shear diagram, okay? So these applied bending moments, they produce 0 shear. So let's start at the beginning of the beam. You have positive 15,000, so that's gonna bring us up 15. Okay? And then nothing happens, nothing happens, nothing happens. 20,000 brings you down. So now we're at negative 5,000, right? And I'm drawing sloppy, but I'll show you the answer in the back. 20,000 brought us down. Then nothing happened, nothing happened, nothing happened until the end. 5,000 pushed us back up. Okay? So boom, just like that, this is the shear diagram. Okay? And we verified it here. And that's just a nicer look. Forget about these numbers for now. Now that we have the shear diagram, now we can get the bending moment diagram. Okay, bending moment, these bending moments will push you up or down. Okay, and shear will, it creates like a, you take the integral, right? So if it's a point force, that means you're gonna get a linear load in bending moment. So check this out. In this case, you have a counterclockwise 20,000. I think I spit it right here, whatever. You have counterclockwise 20,000, okay? Now on the bending diagram, a counterclockwise pushes you down, okay? I know counterclockwise is usually positive, so you might think, oh, I'm going up 20,000, but no, that's not the case. When you do the diagrams, a counterclockwise moment will bring you down. So we're gonna start at 20,000, okay? Negative 20, oh, damn, my bad. Anyways, 20,000. And then, give me 1 second. Yes. So this is why these numbers were important. Prior to doing the bending diagram, give me 1 second. Let me go ahead and restart it right here. The shear will create a linear distribution for bending, okay? In this case, it's a point load, right? These points, these forces, reactions, they're gonna create linear distributions for shear. And they did. Then that's a linear relationship, right? Then you take the integral of that, you're gonna get a triangle. So that's how you do bending moments. In this case, the distance of the total beam is 6 meters, right? So let's go ahead and put that. 3 meters, 3 meters, okay? Let's just keep it like that for now. So you get the area. 15,000 times 3, that's 45,000, okay? Now, because we're above 0, this is a positive number. 45,000 positive. Let's do the same for this one. 5,000 times 3, that is 15,000. And because we're under 0, that's a negative, okay? Now, we started here at negative 20,000 because it was a counterclockwise moment. So now, let's go ahead and do this. This is a positive slope. So that means the integral of a line, it's like, imagine this was y is equal to 5x, right? Well, I'm sorry, y is equal to 5, right? That's just a y function. It's just straight across. So take the integral, you get y is equal to 5x, right? The integral is going to be a line either going this way or this way with a slope 5. But which one is it? But in this case, we know it's positive. It's above 0, so that means this is our line. So we are going to go 45,000. We're going to end up at 25,000, right? If we start at 20 in the negative, we'll end up at 25 in the positive because we're going 45,000. We're going halfway throughout the beam, and the line's going to go from here to here. That's a slope of 45,000. I'm sorry, that's a slope of 15,000. So every meter, it's going up 15,000. 3 meters, right? 15,000, 15,000, 15,000, right? That's all that is. Then, what else is happening here? There's a counterclockwise 20,000. So that means we're going to come back down. And this is negative 5,000. So that means we're at this point. And then we're going to go negative 15,000, okay? So when you go negative Oh, I'm sorry, hold on. 20,000 wouldn't bring you a negative 5,000. It will bring you to a positive 5,000. Went too fast there, man. My bad, my bad. But I'm doing this as I go, okay? So please don't judge. 2, 3. There we go. This 20,000 would have brought you down from 25,000 to 5,000. And then this slope is negative 15,000, right? And it goes for the rest of the beam from the next 3 meters. So up to here. So you're going to have minus 15,000. Now we're going to use this line, right? Because it's a negative, right? That's what that negative means. So we're going to go down 15,000. That's going to bring us to 10,000. Okay, now we're here. Then finally, that 10,000 is clockwise, so that pushes us back up. Okay, remember, clockwise pushes you up, counterclockwise pushes you down. Okay, and boom, there you go, man. That is our bending moment. Easy money. And that is just a nicer look of it, okay? So the reason you do these problems, that's it, guys. That's the whole problem. This is the front page, the back page, and that is the front page. So the reason we do these problems is, at this point, guys, the reason I like to say this at the end of the videos is because you're probably wondering, what the hell did I just do? I'm in college. I don't care about all this. I just want to get an A, whatever I get it. You know, I was there. But it's really useful because you need to know why you're doing these kind of problems to begin with. In this case, you are analyzing a beam that was already sized. They already chose the material for it, right? They chose steel. They chose the inertia, meaning, you know inertia, meaning you know the cross-section, right? In order to get this property, you need to know if it's an I-shaped, a T-shaped, a circular beam, whatever the case is. You know there's going to be a 20,000 pound force. Well, why? Well, maybe that's just the way it was designed, right? Maybe they tell you, hey, I want you to, we're designing an airplane, right? Let's pretend this is a beam on an airplane, like a wing. Hey, and it wouldn't be fixed. It would just be fixed at one location, right? Because it's a wing. They'll be like, hey, you know, we're designing this plane. We're looking to put all these radios and all these engines and all these cameras in there. And at the end of the day, you know, we're looking to put we're looking at maybe it's going to weigh maybe 40,000 pounds or newtons, kilonewtons. Okay, 40,000 newtons. Well, half of the plane, maybe this wing might take 20,000 newtons and the other wing might take 20,000 newtons. So you have to design, in this case, they already designed it actually. So they designed a cross section for that wing saying, hey, 20,000, and there's probably a moment being acted. That's not going to happen, right? But there's probably a moment acting on it. Can my beam support it? What's my displacement looking like? What's my angle looking like? The slopes, right? And these are kind of just checks. In previous classes, like statics, not even statics, more like strength of materials, where you have to find like normal stresses, shear stresses. Those are better problems in my opinion, but you've already passed those classes. It is what it is. In this case, you really are just doing checks. Hey, look, this is how much internal force is being produced on my beam. I have to make sure that it could withstand these loads. And these are just checkpoints, right? Yeah, it can. Look, my beam is made of steel, has this cross-section. Yeah, it's going to withhold just fine. Oh, no, it's not. Hey, can you change this cross-section? Can you change the material? Yada, 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 whatever that is. But yeah, aside from that, that is the answer on this one. I hope you guys learned, and good luck on that exam.